Let's investigate the tensor products of Pauli matrices. First, let's have a look at a general 2x2 matrix with complex entries. We can write that as A2 is an element of the matrices which are 2x2 and which have complex entries. And I'm using this bold-face C to denote the complex numbers. So we have a 2x2 matrix that's 4 entries, and all of those entries are complex numbers. So a special case of this would be a real-valued 2x2 matrix. And this matrix is a square matrix. We can actually write this matrix A2 as a linear combination of the Pauli matrices. We have to include the identity matrix as well. So here is what we're going to do. We're going to write A2 as the sum over some index, and I'll choose the index k. K is going to go from 0 to 3. And in this linear combination, we're going to have coefficients, and the coefficients are going to be called alpha sub k. So we're going to have 4 of these coefficients, because k goes from 0, 1, 2, and 3. So 0 is going to correspond to the identity, and 1, 2, and 3 are going to correspond to the Pauli x, y, and z operators. And I will write all of these matrices as sigma sub k. So sigma will be this general notation, and this index will specify which one of these matrices we are specifically talking about. So let's write out this linear combination in full. We're going to have alpha 0, sigma 0, alpha 1, sigma 1, alpha 2, sigma 2, and alpha 3, sigma 3. So that is 4 terms in this linear combination. And we can write this in a slightly different notation. Instead of this sigma notation, we can write this with capital letters. So this is going to be I, the identity, alpha 1 times Pauli x, alpha 2 times Pauli y, and alpha 3 times Pauli z. So you can see that there's 2 ways of writing these matrices. And all 4 of these matrices, I, X, Y, and Z, they are 2x2 matrices. They are Hermitian and they are unitary. And if you take the square of any of these 4 matrices, you will get the identity. So this works for any general 2x2 matrix with complex entries. But now the problem is finding these coefficients. How do we turn a known 2x2 complex valued matrix into these 4 numbers? We want to turn this into coefficients. We want to translate it into the language of this basis. You can think of these guys as an orthonormal basis for these matrices. So these are basis vectors. We're used to thinking of vectors as columns or rows, but matrices can also be vectors. Any object that satisfies the axioms of a vector space can be actually described as a vector. And what is additionally interesting is that this kind of mathematical structure also satisfies the inner product space axioms. So we can actually define an inner product space. And we're going to use an inner product to find these coefficients. So I'll write that over here. These alpha k coefficients can be written as 1/2 of the trace of the product of this arbitrary matrix A2 with one of these sigma k. It has to be the same sigma k that we have over here. So this is the same index. This is actually shorthand for 4 different expressions. We have one for k equals 0, 1, 2, and 3. And we could actually put a Hermitian adjoint sign over here, but that would be redundant because all of these guys are Hermitian matrices. This trace of a product of 2 matrices, this is actually given the name the Frobenius inner product. So that is one way to call this kind of mathematical structure. And the Frobenius inner product takes in 2 matrices as an input, and it spits out a number. So we have to do matrix multiplication, and in general, we also have to take the Hermitian adjoint of one of these matrices. So a matrix with the Hermitian adjoint of another matrix. We do matrix multiplication to combine them, and that gives us another matrix. So inside the brackets, we have a matrix. And then we take the trace. And the trace is the sum of all the diagonal entries of that matrix. So that is what we have in this situation over here. And what is going on with this factor of 1/2? That is a normalization coefficient. Let's consider a special case. What happens if A2 is equal to one of these sigmas? So let's say it's any one of these sigmas, and for our purposes, let's call it sigma k. So if we set A2 equal to sigma k, then we're going to have sigma k times sigma k. And sigma k times sigma k, that's also the same as sigma k times the Hermitian adjoint of sigma k. And that can be also written as sigma k squared. But earlier I mentioned that if you take the square of any of these Pauli matrices with the identity, you will get back the identity. So that means on the inside, we should have the identity for this special case. So that means if we take the trace of sigma 0, which is the same as sigma 0 squared or sigma k squared, that is going to be equal to 2. Because the 2 by 2 identity matrix just has 2 diagonal elements. We have 1 and 1. We're just adding the diagonal elements. We're taking the sum of all the diagonal elements. That is what the trace is doing. So we get 2 over here. And we have to compensate by dividing by 2. Because we want the inner product of sigma k with itself to give us 1. We don't want it to be equal to 2. So that is the reasoning behind this normalization factor. And now we have a tool set that allows us to take any 2 by 2 matrix with complex values, and we can express it as 4 coefficients. And we can treat those 4 coefficients as the entries in some kind of column vector. So we're actually dealing with a vector space. These guys are the entries of a vector. And they can directly be mapped back to this matrix over here. So that is what we've got for a single qubit Hilbert space. You can think of this as a 2-dimensional Hilbert space. All of these guys can be thought of as matrix representations of operators which act on a 2-dimensional Hilbert space. That describes a single qubit by itself. Let's take an example. So I'll take an example below here. So an example, which we've seen in previous videos in the quantum mechanics playlist, is the Hadamard gate. So what I'm going to do is I'm going to take this inner product over here, this normalized version of the Frobenius inner product, and I'm going to find what the coefficients are for all of these guys. So if we take 1/2 the trace of the Hadamard gate with the identity, well, this is just going to give the Hadamard, and the Hadamard actually has a positive sign on one of the terms in the diagonal and a minus sign on the other terms of the diagonal, so they actually are equal and they will cancel. They're equal in magnitude but opposite in sign. So that's going to give us 0. So this factor of 1/2 is not even going to matter in this case because we're just going to get 0. And we're also going to get 0 if we take the trace of the Hadamard gate multiplied by this Pauli y operator. So those two coefficients are going to be 0. So that's the alpha 0 coefficient and the alpha 2 coefficient. But we will get non-zero coefficients as well. If we do 1/2 the trace of the Hadamard with the Pauli x, that's going to give us 1 on square root 2. And if we do 1/2 the trace of the Hadamard with Pauli z, that is also going to give us the same value. So both x and z are going to have the same coefficients. And keep in mind that I can actually put a Hermitian adjoint over here and write this as the more general Frobenius inner product with an extra factor of 1/2 for normalization purposes. But it is redundant to put that Hermitian adjoint sign because all of these operators are Hermitian. Even the Hadamard gate is Hermitian over here. But in general, this A2 does not have to be Hermitian. It is an arbitrary 2x2 matrix with complex values. So this over here gives us all the information we need. And we can actually write this Hadamard gate as the linear combination. We're going to have 0, I, plus 1 on square root 2 x, plus 0, y, plus 1 on square root 2 z. And we can write that more compactly. We can write the Hadamard gate as 1 on the square root of 2 of x plus Z. So this over here is the bit flip, and this is the phase flip. If we add a bit flip and a phase flip together, we're going to have the Hadamard gate up to a normalization factor of 1 over the square root of 2. So we've taken a familiar example, which is the Hadamard gate, and we've decomposed it into this linear combination of Pauli matrices. And we also have to include the identity operator here. So that is a special case. And we can see that this over here is normalized. It can be thought of as a normalized vector. Because if we take all of the coefficients and we square them and then add them together, that's the procedure of normalization, we would have 1/2 from here and 1/2 over here. And 1/2 plus 1/2 is 1. So we just have to square those coefficients and add them together. And that is how we can see if it is normalized. And over here in this example, it is normalized. That is why it is necessary to have this coefficient out the front. So you can see why normalization is very important. It makes everything so convenient because you don't have to keep dividing by these miscellaneous factors. Now we've worked with a single qubit Hilbert space. Let's generalize this to 2 qubits. So let's write down an arbitrary matrix, which I'll call A sub 4. This is going to be an element of the 4x4 matrices. So the same format over here with complex entries. And I'm also using boldface C to denote the complex numbers. A special case of this would be the 4x4 matrices with real values. So this is what we're dealing with. Let's do something similar to what we have up here. So we can write this A4 matrix as the double sum. We're going to need 2 indices. We're going to sum K1 from 0 to 3, and then we're going to have another sum over here, and it's going to be K2 going from 0 up to 3. And we're going to have coefficients which are specified by 2 indices, which is K1, K2, and over here we're going to have, instead of just these Pauli matrices, we're going to take tensor products of Pauli matrices. So we'll have sigma K1 tensor product sigma K2. So this is our linear combination. Over here we had 4 basis vectors in our orthonormal basis. Now we have 16 basis vectors in an orthonormal basis. So that's because we have these 2 indices, and both of these indices go from 0 to 3. That's 4 possible values, and we have 4 times 4, and that's 16. So we have a lot more possible basis vectors that we would need to evaluate this type of inner product. But this inner product doesn't work. We have to generalize it. So we have to do an alternative inner product. So if we want to find one of these coefficients, alpha K1, K2, which is specified by 2 indices, we have to take 1/4 of the trace of A4 with one of these basis vectors, which is the tensor product of sigma K1, tensor product sigma K2. So that's what we have on the inside over here, and I'll close this bracket. We could also put a Hermitian adjoint over here, but this is Hermitian. We're taking 2 Hermitian operators, taking the tensor product, that is also going to be Hermitian. So this is our basis vector. It is analogous to this sigma K, but now we have 2 indices to specify this. So A4, what kind of object is this? This is a 4x4 matrix with complex values inside it. And this object over here in the brackets, this is also a 4x4 matrix, which we've constructed by taking 2x2 matrices and taking the tensor product between them. So we're taking these Pauli matrices and the identity, and we're doing a tensor product, and that's going to turn 2 separate 2x2 matrices into a single 4x4 matrix. And we're using these guys as orthonormal basis vectors to construct these coefficients. And you can see that this can also be thought of as a vector. And this vector will have 16 entries. So that vector up here had 4 entries, but now we have 16 entries. And many of those entries will be 0. Only some of them might be non-zero. So this over here is how we can use the Frobenius inner product. But why do we have a factor of 1/4 instead of a factor of 1/2? Well, imagine the reasoning that we had up here. Well, what we did is we took one of the sigma k's and we set A2 equal to the sigma k. And that gave us sigma k squared on the inside. And we know that sigma k squared is the same as the identity. So if we take the trace of the identity, we end up getting 2, because this is a 2 by 2 matrix. And it is the identity matrix, which just has 2 1s along the identity. So we take the sum, and that gives us 2. But what's going to happen over here? If we use similar reasoning, we can set A4 equal to this tensor product of sigma k1 and sigma k2. And that's going to give us the square of this. So we're going to have sigma k1 squared and sigma k2 squared. So what we're going to end up with is the identity operator, tensor product, the identity. So what is the trace of that? Well, the trace of sigma 0 tensor product sigma 0 is equal to 4. Why is this the case? Well, we're dealing with a 4 by 4 matrix. And this is the 4 by 4 identity matrix. It's going to have zeros everywhere except along the diagonal. And the diagonal is going to have 4 elements. It's going to be 1, 1, 1, 1. And when we take the trace, we're going to sum all 4 of those 1s, and that's going to give us 4. So if we want this to be an orthonormal basis, and if we want the result of that substitution to give us an inner product value of 1, we need to compensate for this 4 by dividing by this factor of 4. So that is where the normalization coefficient comes from. Now, let's do an example. We're just going to do one more example, and then we'll finish up the video. So the example that I'm going to use over here is the swap gate. The swap gate is actually a very neat example for this, because we're only going to need one index. So this is equal to 1/2 of the sum of identity, tensor product identity, x, tensor product x, plus y, tensor product y, plus z, tensor product z. So I am omitting the tensor product sign. That is this little circle with an x on the inside. And I can omit this little tensor product sign because from the context, it is clear what we're doing. We're not multiplying I by I or x by x. That is not what this notation is telling us. Usually, if you have two matrices next to each other, that means that those matrices are being multiplied, or they're both being applied to the same state. But in this context, this is just shorthand notation for the tensor product of two of the Pauli matrices. And you can see that this can be written in this notation. We can write this as the sum over a single index k that goes from 0 to 3, and all of these alpha k, all of these guys are going to be 0 except when this index is equal. So it's only values where k1 is equal to k2 that we care about. So all of those values are going to be 1/2, and then we're going to have the tensor product of k with itself. So we have sigma k, tensor product, sigma k. And this value of alpha kk, well, that's just equal to 1/2. So we have 1/2 as the coefficient of all 4 of these combinations. In total, there are 16 combinations. So all the other combinations have coefficients equal to 0, but these are the only non-zero coefficients. So this is another compact way to write it. And this is the swap gate, and in another video in the quantum mechanics playlist, we saw the matrix representation of this swap gate. An exercise that is good to do is to individually write out the tensor products of these matrices, and then add the matrices together. And then you will see the matrix representation emerging. So this is a very neat way of writing down the swap gate. So a very important point, when you see this type of notation occurring over here, in this context, if you have something like the identity, then the identity next to it, that is the same as the identity tensor product, the identity. You can also write that with the sigma notation. Sigma 0, tensor product, sigma 0. So that is what's going on over here. We're just doing a condensed notation for this representation. So we've seen how this works for a single qubit system and a 2-qubit system. You can also generalize this to multiple qubit systems. And what you'll notice is that the normalization factor is going to be equal to 1/2 to the n, where n is the dimension of the Hilbert space. Here we have 1/2 to the 1, 1/2 to the 2. We have 2 squared. So over here we have 4, and then we're going to have 16, and then we have higher powers of 4 as the number of these orthonormal basis vectors. In the next video in the quantum mechanics playlist, we're going to see the representations of 2-qubit gates in terms of these Pauli matrix tensor products. And And we're going to use those representations to prove some of the circuit identities that we've seen in other videos in the quantum mechanics playlist. You can find all those videos if you click over here.